Thank you all for being here today. In this presentation, the title is Introduction to the GIL for the Python beginners and disabling it in Python 3.13 and leveraging concurrency. I will explain the basics, global interpreter lock, GIL for the Python beginners, and I will show how it enables parallel executions. Here is today's agenda. First, I will explain the basic brief glossary of key terms, and I will introduce constraints of imports by GIL, and explain our approaches to overcome these challenges. And I will share some real-world use cases to use disabled GIL. This presentation is especially targeted for the Python beginners who has never used disabled GIL before. The goal of this presentation is to understand the relationships between the multi-threading and multiprocessing and GIL. And my hope is everyone here to become interested in using the disabled GIL and to start the using after this presentation. Let me take a moment to introduce myself. My name is Saito from Japan, and I am currently working as a solution engineer for Azure, and I hold a master's degree of engineering, and I major in the bioinformatics. During my research, I used machine learning, and after them, I became interested in the Python. So now let's dive into today's presentation. This is the status of the Python versions. As you can see, the Gantt chart, as of today, the Python 3.13 is the latest version of today. The version is released last October. And the next version, Python 3.14, is as of currently released, but the version is better. So I will focus today Python 3.13 in this presentation. First, I will talk about the brief historical background of Python performance, performance optimizations. Prior to Python 3.13, GIL relies on there is several approaches to optimize Python performance. The main approach was to using the multi-threading and the multiprocessing. However, multi-threading is subject to locking system called the global interpreter lock, GIL, so which makes it difficult to fully optimize. However, Python 3.13 and later versions, new approach had been added. The new approach is disabling GILs, which allows true parallelisms. At first, I will explain how to use the disabled GIL. This is an easy way to start the disabled GIL. The Python 3.13 with disabled GIL can be downloaded from the official site. When downloading, don't forget to check the checkbox. This one. The checkbox is a free thread binary checkbox. After downloaded, you will find you will get the two executable files. In case of Windows OS, you will find the python.exe file and the Python 3.13t.exe files. The latter one with Python 3.13t file is the interpreter with disabled GILs. So all you have to do to use the disabled GIL is select this interpreter and run it. Next, I will briefly explain the three main, important points, key terms necessary to understand this presentation. First key term is multithreading, and multithreading is characteristic of thread scheduling. And it allows switching between the multiple threads in single process. The orange bar, it means CPU-bounded tasks, and the the light green bar means non-CPU-bounded tasks. As you can see the graph, the multithreading cannot run at the same time. This is a characteristic of the multithreading in terms of the Python. So yeah, I will explain later why these things happens. Second key term is multiprocessing. Multiprocessing is characteristic of parallelism. It allows a multiple process to run the same program. The figure shows how multiple processes run in the parallel. As I mentioned before, the orange bar is CPU-bounded tasks, and the light green bar is non-CPU-bounded tasks, like IO waiting time. So compared with multithreading, I mentioned before, the multiprocessing run the CPU-bounded tasks, the orange bar, at the same time in the single program. The third key term is global interpreter lock, GIL, and this is the main topic of this presentation. And GIL is implemented for the thread save. GIL ensures that only one CPU-bounded task is running in the single process. In the graph, the orange bar, this one, can run at the same one time at the same time and will be affected by the GIL. And the light green bar, like non-CPU-bounded tasks, will not be affected by GIL. Why does this GIL enforce these restrictions? Of course, there are some merits to use GILs. I will explain the merits and demerits in the following present slides. As far as merits are concerned, GIL provides simple, effective thread safety. And GIL also prevents race conditions. And GIL also avoids unexpected behavior and data corruptions. So you don't need to implement the complex mutex on the program side. On the other hand, as far as the demerits are concerned, the GIL limits multithreading and reduce the performance in the CPU-bounded tasks. So even if you use high-spec CPU multi-core processors, you don't fully utilize it. This is a demerit of the GIL. Yeah, here is an example of how GIL can actually degrade the CPU-bounded multiprocessing performance. As an example of CPU-bounded tasks, I select the calculation of Fibonacci numbers. The left bar is the result of the single threading, and the right bar represents the multithreading. Ideally, multithreading is faster than a single thread. However, as you can see the graph, it takes about the same time between the single threading and the multithreading in Python program. This is because GIL allows only one thread can show, this result showing the GIL restricts demerit, when it comes to the optimizing the Python performance. To overcome these GIL constraints, there are some approaches. multiprocessing and asynchronous processing and third-party libraries had been used in the past. However, starting from the Python 3.13, a new approach had been added. The new approach is, as you already know, using the disabled GIL. And now I will describe each of the new approaches to overcome GIL constraints. The first approach to overcome GIL constraints is using the multiprocessing. The use of multiprocessing is particularly suited for the CPU-bounded tasks. The graph shows an example of how long the CPU-bounded task took time. In the graph, the left bar, this bar, is single processing, and right bar is multiprocessing. As you can see the graph, the multiprocessing takes less time compared with the single processing. Although multiprocessing is good for the speed improvement, but CPU-bound processing, it also has a demerit. This is memory usage, and inter-process communication costs are high. This is because, as shown in the graph on the right, each process has its own CPU resources and memories. This is different from the multithreading. In case of the multithreading, each thread shares the CPU resources and the memory between the multithreading. The second approach to overcome GIL constraints is to use the asynchronous processing. A particularly well-known Python library is async.io. Async.io does not block threads while waiting for the I/O operations like network connections and file I/Os and database access. So you can run the program in one thread with async.io like the graph. The left graph is multithreading, and the right graph is a single thread with async.io. It looks good, but if there is no I/O waiting time in the single thread, it would just be a single thread. So therefore, async.io is not suitable for the CPU-bounded tasks, but it's very powerful for programs with I/O waiting, which has a long time I/O waiting time. Here is an example that shows the power of async.io in practice. In this case, an example of I/O waiting I/O operations, I selected the sleep functions. The left bar is synchronous processing, and the result takes about 6 seconds. This is because synchronous processing runs in order. On the other hand, the asynchronous processing, it takes only 3 seconds. This is because each process in parallel. The third approach to overcome GIL constraints is to utilize the C and C++ implemented third libraries. Since GIL does not C and C++ exist, so libraries can be used without being affected by GIL. For example, Python, NumPy, Pandas, PyTorch, Scikit, scikit-learn, and SciPy are examples of these libraries. And the fourth and final approach to overcome GIL constraints is the main topic, using the disabled GILs. In Python enhancement proposal PEP 703, the new option disabling GIL has been proposed. The figure shows the enabling GIL on the left side, and the right side shows the disabling GILs. As you can see the graph, without GIL, each thread has directly access the OS thread schedulers. This makes the CPU core allocations for each thread and achieves and realizes the to-do parallelisms. Here is an example of the to-do parallelisms with disabled GILs. The graph compares the execution time for for CPU-bounded tasks. The left bar is enabled GILs, and the right bar is disabled GILs. As a result, processing with enabled GILs about 4 seconds to execute. Compared with that, disabled GILs takes about only 2 seconds. This is because with disabled GILs, to-do parallelisms is realized. So this means disabled GIL is much faster than enabled GILs. Thus, disabling GILs can improve performance. The graph shows the example of the execution times and enabled GILs and disabled GILs in the CPU-bounded tasks. In this case, bucket sorting and fractal generations and prime factors are examples. As you can see in the graph, disabling GIL on the right takes less time compared with the enabled GILs on each scenarios. However, disabling GIL in Python 3.13 is experimental, so speeding up improvements varies depending on the programs, and does not necessarily guarantee the faster processing. And in some cases, may result in the slower processing compared with the multi-threaded programs with enabled GILs. In this slide, I will talk about overview points to consider when use disabled GILs. Among the various points to consider, the main points to consider are extension modules and potential race conditions. As far as extension modules to be used, it is necessary to check the libraries are thread safe. And as far as potential race conditions, it is needed to check the synchronization provided. And I will explain each of the consideration in detail. The first consideration point is extension modules. It is necessary to check the version of the library you use. Since extension modules is developed based on the thread safety of the GILs, so some module versions may not support and does not work as expected when GIL is not disabled. Specifically, when using the modules such as Python, NumPy, Pandas, PyTorch, scikit-learn, SumPy, described in the table, it is necessary to check you use the supported version of the library. The second consideration point to consider is race conditions. It is necessary to avoid using global variables and use mutex when implementing the program, since disabled GIL might manipulate various points in other threads. There is one example to show the race conditions. The program is count number in 5 threads, and each thread counts by 10,000. So as you can anticipate, each thread, 5 threads can count the 10,000, so the total amount of count number would become 50,000, like this. And when you run this program with enabled GIL, the result would become 50,000. But if you run this program without GIL, the result would not become 50,000. This is a consideration point of race conditions. So far, I have explained that disabling GIL has the potential to optimize the Python performance, but there are some consideration points. In this slide, I have organized the good and bad points of each multi-threading and multiprocessing and disabling GILs. The table shows the disabling GIL is the only approach to realize both of the easy data sharing and true parallelisms. As you can see, multi-threading or multiprocessing cannot meet these items at the same time. As I said in the previous slide, easy data sharing and true parallelisms are key items to consider to use the disabling GILs. So I have organized the two dimensions graph by them. The horizontal axis is easy data sharing and vertical axis is true parallelisms. As you can see, if you need to the only true parallelisms, multiprocessing is enough and appropriate. And if you need to meet the only easy data sharing, you should choose multi-threading, and that is appropriate. And if you need easy data sharing and true parallelisms, you should choose. You can choose disabling GILs. This is appropriate choice. Now that I have explained that disabling GIL is the appropriate scenarios for requires both easy data sharing and true parallelisms. Here are some examples of the specific scenarios where disabling GIL is recommended. For example, ETL processing and image processing, log analysis, real-time analysis, such examples. And all of those scenarios requires both easy data sharing and high-performance computing. Therefore, I encourage everyone to use disabling GILs in these scenarios. Finally, I summarize this presentation. There are conclusions. Number one, disabling GIL is a new approach to optimize performance from Python 3.13. And two, GIL offers some merits, but it limits multi-threading and prevents using the old CPU core effectively. Number three, when using the disabling GILs, you should consider variable extensions and race conditions. Number four, disabling GIL is especially valuable for CPU-bounded tasks that requires data sharing and true parallelisms. That's it. That's the conclusion of this presentation, and I hope that everyone here becomes interested in using the disabled GILs and actually using them from now on. Thank you for listening to my presentation.
Okay, we have much time. So let's check the first question. At this stage, have there been any practical difficulties in adapting Python with the disabled GIL?
Yes, so as mentioned in the presentation, the practical difficulties is to consider the locking system on the program side. This is because GIL, enabled GIL is makes the developers implement Python programming more easily without thinking too much complicated things. However, if using the disabled GILs is accessing the same amount of the same memory have to be it should be so that in practicable, yes, you should implement the locking system.
Okay, thank you for your answer. Now the next question, could you explain what is easy data sharing?
Yeah, easy data sharing is can access the memory as different settings. So in case of the multiprocessing, if it is needed, to share the data is needed to communicate with the inter-process communications. So it takes some cost. On the other hand, in case of the multi-threading, without such a inter-process communications, data so it's easier to access the memory from the different thread.
Okay, thank you for your response. Now the next question, at this stage, have there been any practical difficulties? Oh, it's all error. Okay. Next one. When using Python with GIL disabled, should we take more care of something when writing the Python code? Example, to make sure to use straight-in .lock.
So yes, let's see. I'm just thinking. So sorry, please skip these questions.
Okay. My next question. How does disabling the GIL perform compared to other methods, like async IO or third-party libraries?
Let's see. So in this in this presentation, I show some result data that was calculated and computed in my local machine. So if you use other environments, the result will might be different from the result. But in case of this presentation, I compared this performance in my local computers.
Okay, we appreciate your response. Okay, this one. How does disabling the GIL perform compared to other methods like async IO or third-party libraries? Is that? So is that one? Okay.
Oh, okay. Oh.
That's interesting. Is there any question from the floor? No, any questions here? Okay, let's thank the speaker.